Okay, good morning, students. We're going to start our discussion, which is about momentum. And we need to start by defining the term momentum. What do you know about momentum? I think you remember the definition of momentum from your grade 9 course. Is there anyone who remembers the definition of momentum? Okay, momentum is the measure of how hard to stop a moving body. It is a measure of how hard to stop a moving body. When a body is moving, at least it possesses momentum. And this momentum is the ability of an object to pertain or to continue its motion. Therefore, when we say momentum, its value can be expressed by the product of mass times speed or velocity. Then when a body with mass m or for any object that have mass and speed, then we can get the product of mass and speed, and this magnitude is called a momentum of moving body. Therefore, momentum is the ability of an object or an unstoppability of a moving object. When a ball is kicked, it possesses momentum, and to stop its motion, yes, it needs to act against its motion, and the hardness or the unstoppability of an object is called momentum. And a momentum is divided into a linear momentum and angular momentum. For a body moving on a straight line or for a linear motion, then the momentum is called linear momentum. Whereas when a body is in rotational motion, then the momentum is called angular momentum or rotational momentum. But before this, we are going to look the angular momentum. Let's revise some points about linear momentum. Linear momentum, the magnitude of linear momentum is the product of mass and velocity, and mathematically can be expressed as P equals mv, where P is linear momentum and m stands for mass and v is for velocity. And this linear momentum by itself is a vector quantity, and the direction is towards the direction of velocity. The direction of momentum is in the direction of velocity because we have two vector quantities, momentum and velocity. Since mass is scalar quantity, then the direction of momentum will be in the direction of the velocity of an object. Therefore, it's a vector quantity. Momentum is a vector quantity. And there is some conservation of laws that relates with linear momentum. For a certain condition, we need to consider the magnitude of momentum, whether it is increasing or decreasing. Then if it remains constant or if it doesn't change throughout the condition, which means if the initial momentum and the final momentum remains the same, then we can say that the momentum is conserved because no change on its magnitude. Then this condition is called law of conservation of linear momentum. According to law of conservation of linear momentum, in the absence of external force, if no external force is acting on an object, then the magnitude of linear momentum remains constant. In the absence of external force, linear momentum remains constant, which means momentum before, for example, if we're considering two bodies and if they are initially moving in opposite direction, then if they are taking the motion on the same line, they will collide. Then when they collide, in the absence of external force, the initial momentum of the two bodies and the final momentum, which is after collision, remains the same. It remains the same. Or mathematically, if there is no net force, for example, I think you remember this expression, which is change in momentum. And when change in momentum is divided by time, which is a fraction of maybe second during collision, then this gives force. Because change in v over change in t is acceleration, and mass is constant before and after collision. If we are dealing with a constant mass, then this gives a net force. But what if the net force is zero? If a net force is zero, what can you say about this result? It becomes zero because there is, we said that there is no any external force that acts on an object. Then we're left with mass times change in velocity over change in t becomes zero. Then if we rearrange, it becomes mv equals zero. But when you say m delta v, it is m times v final minus v initial, it becomes zero. Then when we multiply m times v final minus m times v initial, it becomes zero. But this m times v final is momentum final equals, when we bring mvi into the right side, it becomes m times v initial. It becomes m times v initial becomes p initial. Then when initial and final values momentum becomes constant, then this condition is called law of conservation of linear momentum. Therefore, momentum is conserved. We can say that momentum of the two bodies, or momentum of the system as a whole, is conserved. Then if the linear momentum is conserved, then the initial momentum and final momentum remains constant. And as this condition will happen when there is no any external force. If external force is zero, then linear momentum becomes constant. The value of linear momentum before and after the system or after collision remains the same. And the second kind of momentum is momentum of a rotating object, or momentum of an object which is moving on maybe a curved path or circular path. For example, the angular momentum of a body of moment of inertia I rotating with an angular speed of omega is given by L equals I times omega. Just as we remember, the linear momentum expression is P equals M times V. For angular momentum, instead of M, we can use I because rotational equivalent of mass. And instead of V, we can use omega because omega is the rotational equivalent of V, or the rotational equivalent of linear velocity. Then we have two momentum. The first one is momentum of a moving object when an object is moving on a straight line, and the second one is the momentum of a rotating object. Then the expression is L equals I times omega. This is a mathematical expression for angular momentum. This is angular momentum. Angular momentum. And the other point on this, on the top of this, is it is a vector quantity. An additional information about angular momentum is as a vector quantity. It's not a scalar quantity, so it needs a direction, and the direction is in the direction of angular speed. And its unit is kilogram meter square over s, and has another expression which is L equals angular momentum equals linear momentum times r. Angular momentum is linear momentum times r, but linear momentum is mass times velocity. Then we come up with the expression mv times r, where mv is a linear momentum, and then when it's multiplied by r, it becomes angular momentum. Therefore, the other expression for angular momentum is p times r, or instead of p, we can use mv, and it becomes mvr. Therefore, angular momentum can be obtained by two expressions. The first one is I times omega, and the other possible expression is m times v times r. These are the two possible expressions for angular momentum. Therefore, as optional, we can use I times omega or mvr can be expression for angular momentum. And this angular momentum also has a conservation of law. But instead of force, we have to think about the torque. When the net torque acting on a body is zero, then the angular momentum has the same value, or the value of angular momentum remains constant. For linear momentum, just a linear momentum to be conserved or constant, the net external force needs to be zero. If no external force acting on a body, no problem. The linear momentum is conserved when there is no net force acting on a body. In similar way, the net angular momentum remains constant if a net torque acting on a body is zero. This one is the first condition. As second condition is angular momentum is constant when the net torque acting on a body is zero. This is the second condition. If the net torque that acts on a rotating body becomes zero, if there is no net torque, then the angular momentum has the same magnitude. Angular momentum, initial angular momentum remains the same value with final angular momentum. Or even we can get the change in angular momentum is zero if a net torque becomes zero. Then if change in angular momentum is zero, this can be expressed as angular momentum final minus angular momentum initial is zero. Then L final equals L initial. But what's L final? It's I final times omega final equals I initial times omega initial. Okay, this one is very important expression for this point. In the absence of external torque or turning effects of force, the angular momentum remains constant. If angular momentum is constant, momentum before and momentum after remains the same. If no external torque for linear motion, if a net force is zero, then linear momentum will be constant or conserved. And for rotational motion, if the net torque is 0, if no turning effect on a body or on a system, if there is no any turning effect on a body, whether the body is in motion or not, that will not be our interest. But if there is no turning effect, then the linear momentum becomes conserved or constant. So these are the criteria to be an angular momentum is constant or conserved. The other point, if angular momentum is constant, then the expression becomes moment of inertia final times angular speed final becomes moment of inertia initial times angular speed initial. Okay, here what we need to understand is we're not said that the moment of inertia and angular momentum is moment of inertia and angular speed is constant. Rather, the product of I times omega remains constant. The product of I times omega remains constant. Not individual quantities, but the product remains constant. For example, if the final inertia increases, then the speed, if the final inertia increases, the final speed will get less. They are inversely proportional. Or if the angular speed in a similar way, if the speed increases, for example, if the final angular speed increases, then the initial the final speed increases, then the final moment of inertia will get less, because to get constant product, then if one increases, the other need to get less. Okay, we have an activity. Okay, we have two activities. The first one is a skater holds her arms outstretched, has a moment of inertia of 5 kilogram meter square, and spins at an angular speed of 5 rad per second. If her moment of inertia is changed to 3 kilogram meter square, when she pulls her arms in, what is her new angular velocity? For example, initially the arms of the skater was stretched out and its initial moment of inertia was 5 kilogram meter square. But when her arms is when she pulls her arms in, or when her arms is closed to her body, then the moment of inertia is decreased, since the mass distribution is compact, and it becomes 3 kilogram meter square. Then these are the moment of inertia of the skater. Then what will happen on its angular speed? Initially, she was moving with an angular speed of 5 rad per second. Then what will happen on her final speed? What do you think? Will it be decrease or increase? Assume the value of angular momentum is constant, or we are dealing with constant angular momentum. We need to apply the law of conservation of angular momentum. Which expression can be used here? Okay. Okay, the given quantities are the initial moment of a scatter is 3, which is 5. I think it is 5 kilogram meter square, and the final becomes 3 kilogram meter square, and her initial angular speed was 5 rad per second, and we are looking to find the final angular speed of the scatter, and the solution is final moment of inertia times the final angular momentum equals moment of inertia initial times omega initial. Since we are looking at this, and it becomes omega final equals I initial times omega initial divided by final inertia. Then it becomes, let's substitute the values. 5 times 5/3, which is 25/3 rad, is greater than or less than 5, which is the increased value. At 8.3 rad per second. Then, since the moment of inertia of the skater has decreased, its angular speed has been increased. Okay, what will be the second solution for the second problem? The problem says calculate the angular momentum of 8 kilogram body rotating with a speed 4 meters per second on a circular track of radius 2 meters. Then here we have provided with 8 kilogram mass. The value of mass is given. and the speed is given, which is 4 meters per second, and the track radius is 2 meters. So we have three quantities. The problem is about a certain body of mass 8 kilogram, and this mass is moving around a circular path of radius 2 meters with a speed of 4 meters per second. So these are an information about the body which is rotating on a circular path, and we are looking to get angular momentum. And what will be the formula for this problem? Angular momentum becomes mass times velocity times r. Now what will be the results that can be obtained? Okay. Then we can substitute the values. For example, for mass is 8 kg, radius is 2 meters, and v is 4 meters per second. Then when these values are multiplied, we get 16. It will be 16 kilogram meter square over second. This will be the angular momentum of a rotating object. Okay, do you have any unclear thing? Have you get any problem? Okay, to summarize, we have said that momentum is the measure of how hard to stop a moving object, which is unstoppability of a moving object. Yes, any object which is in motion is not need to stop its motion, it needs to continue its motion. And to stop, it depends on its mass and speed. If an object is moving with a large speed, it is tough to stop it. And in similar way, for example, if a body is with a huge mass, and will be hard to stop it. And momentum can be linear momentum and angular momentum. When we say linear momentum, it is the momentum of a body when a body is moving on a straight line. Then there is a linear speed, and the product of mass and its speed, the immediate product of mass and the speed gives a linear momentum. And as there is law of conservation of linear momentum, if there is no need force acting on a body, then the linear momentum remains constant. Whether there is two bodies in a system or more than two bodies in a system, before collision and after collision, the magnitude of momentum of the system remains constant. Not the individual bodies, but the system remains constant, and the magnitude will not be changed. The magnitude gets the same value. And formally, we can state that in the absence of external force, the linear momentum of the system remains constant, which means initial momentum and final momentum have the same values. They will be the same value, or they will have the same value. And momentum before and momentum after is equal, and we can say that momentum is conserved. And the second kinds of momentum is a momentum associated with rotating objects. And when an object is in rotation motion, then there is angular momentum, and the momentum is called angular momentum. And this angular momentum depends on the moment of inertia of a body and angular speed of a body in a similar way to that of linear momentum. For mass, we can use moment of inertia, and for speed, we can use angular speed. Then the product of moment of inertia times angular speed gives angular momentum. Angular momentum is the product of moment of inertia times angular speed. This linear momentum or angular momentum in particular, and the whole momentum is a vector quantity, and the unit is for angular momentum, it is kilogram meter square over second. This angular momentum is a vector quantity, as we have said, but the direction depends on the angular speed of a rotating object. Angular momentum can be expressed. We have another ways to express angular momentum, or optional ways, which is linear momentum times r. And angular momentum has two expressions. Therefore, we can express it as I times omega or mbr. It's optional to use one of them just to determine the magnitude of angular momentum. And in similar way to that of linear momentum, angular momentum also can be constant or conserved throughout the motion or throughout the rotating motion. Angular momentum can be constant or can remain the same value. But this will happen when the net torque is zero. If no net torque acting on an object, which means if the net torque is zero. If a force cannot have a turning effect, then angular momentum will be constant, which is called law of conservation of angular momentum. If the body is in conservation of angular momentum, then momentum initial and momentum final becomes constant, and we can say that I initial times omega initial equals I final times omega final. But the net torque need to be zero. And this tells that the product of I times omega remains constant. For example, if the moment of inertia of a body increases, the increment is based on the decrement of angular speed. As angular speed need to be, it should be just less with less value. And we have we have used an example just as an activity. For example, an ice skater can be an example of constant angular momentum. Since the law of conservation of angular momentum says angular momentum before and after is the same, then we can use I final times omega final equals I initial times omega initial. Then we can find the magnitude of one of the two quantities. And also the other option of getting the value of angular momentum is m times v times r. So we have two expressions, we can use them interchangeably. Okay, this is ends of this lesson, and thank you very much.